All right, so part one is done. Now on to part two of another exciting edition of Chemistry Review. You have the periodic table elements. It's fun just to, if you're having a bad day, just stare at the periodic table elements for a few minutes, get your bearings straight, get you a little bit grounded. So we're going to talk about the trends, and it's tough for me not to click on things because I have a PowerPoint here and I really want to click, but I'm not. Last time we talked about atomic radius and how it decreases going this way towards the noble gases because you have the electrons and the protons, more of them in the same space, so they attract and they pull together a little bit more, and then they increase going down because you add the layer. I think that's as far as we got. So let's give you a second here to look at that. Feel free to pause and just stare at the periodic table for a moment if you want. All right, so those trends. Ionization energy. All right, so ionization energy is the energy needed to remove that electron. So we're forming positive ions, those cations. All right, and if you remember, the positive ions are group 1, 2, any of the metals are positive, and group 3, we have a positive ion, so you know they're going to have it. But the same principle applies as last time. So as we go across the periodic table, I'm adding protons, I'm adding electrons for every new element that I add going across, which means there's a greater attractive force there, which also translates to the harder ability, or more energy required to remove an electron, because there's a greater attractive force there. You think Coulomb's law. So the ionization energy does increase going across the periodic table, and it increases going up the periodic table because as you are decreasing layers. All right, just looking at lithium compared to francium. All right, lithium has the 2 layers, and there's going to be a greater attraction for that electron to the protons as it's closer. Again, Coulomb's law, the distance factor there. So it's going to be harder to pull off. And as you get further down here, you have more electrons in the way, so they shield the valence electrons that could be pulled from the nucleus. So again, ionization energy increases going towards the noble gases and going up the periodic table. Next one I want to talk about is, electron affinity, which is the opposite of ionization energy. So electron affinity, which has the same trend as ionization energy, is really looking at how easy it will be for a negative ion to be formed, the energy change in atoms when electrons are added to the neutral atom to form the negative ion, that trend goes across, goes up. Same principles apply. The cations here, they are deficient in that electron, and it's easier for them just to remove them than adding a whole bunch. And then finally, we have electronegativity, which as a trend itself I see it more as a diagonal. It's kind of a progressive one, not really a quantitative one. But electronegativity increases going up and to the right. With fluorine being the greatest, you kind of eliminate the noble gases. The reasoning there, you don't really have to know, but do know that trend. I feel like I'm forgetting one. The ionic radius and size is a little bit different, but I don't have that here. I think you're good. All right, moving on. Electron configuration, and these are looking at the last electron, and that would define it. So, for instance, hydrogen is 1s1. But as we get deeper into the periodic table, right here, you'd have everything before it. 1s2, 2s2, 2p6, 3s2, and it's just that pattern that repeats itself over and over. So this is kind of like the final one in the listing. So you could say, oh, it's got the electron configuration of that noble gas plus whatever is here. I really doubt the College Board asked you an electron configuration question, since you can just type it into your computer real quick and figure it out, or look in the back of a book. They may ask, I don't know, actually I don't even know what, but I really don't see this one being on there. Also be aware of electron configuration of ions. So, if I'm looking at lithium here, the ionic form of it, the ion would be 1s2. But the ions are going to form the noble gas configuration because they're more stable there. And then finally, more likely to be on there would be photoelectronic spectroscopy, or PES, which is chlorine. Remember the big thing here, the axes, looking at the units and the numbers, it's kind of reverse what you're normal to. So you've got a higher number on the left, where we're used to being at closer to 0 on this axis, and over here, on the right, you've got the lower number. And this is just the energy required. Looking at the energy it takes to remove electrons at certain areas, right? So as I add energy, right, starting from low going to high, I get a few electrons that spike out here. All right, so this peak tells you the intensity, or really the relative amount of electrons, and the x-axis is telling you how much energy. These problems, I approach it from looking from the core electrons. So if you look at the left, right, this will be the shell that's closest to the nucleus. In the case of chlorine, it's going to be that 1s2 shell. All right, it's got just 2 electrons, so you get the height here. Right, they're all equal. So that's going to be the 1s2 shell. And often you'll be asked to identify which shell is which, or comparing two elements to see which graph is which element. But if you start here, the core ones on the left, then you work out, that's the 1s2, and the next area working out would obviously be 2s2. And then next to it's this much bigger peak, but the next highest energy would be the 2p6 shell. So you get 6 electrons here, you get the 2 electrons here, so that's the entire second layer shell, right, all the way there. And then moving the next shell, or chlorine will be the 3s2. Again, they got that height of the 2, much lower energy. And then finally, you have the outer shell for chlorine, which has those 7 valence electrons. It would be 3p5. So the valence electrons would be from the s shell, the p shell, add them together, you get 7. But this is the 3p5. Do note that this peak is lower than the peak for the 6 because there's less electrons, but it's just a little bit be nice if I think it is actually half of that, which would be 1. So yeah, not too hard if you've seen it and practiced it a little bit. That should be it for Unit 1. I think the hard stuff there, the molar mass, photoelectron spectroscopy, and explaining the trends. So, you got some problems? Again, ask me questions, you got them. And good luck.